Welcome to yet another class. I'm Dr. B, your chemistry teacher. Today we are going to see how we'll continue from our previous class, the transition state theory. Here we are going to see how we can derive the transition state equation that will lead us to calculate the rate constant of a reaction and also to determine the energy difference, that is the delta H, the enthalpy and entropy degree of what disorderliness of a system. So we're going to look at the transition state equation. The transition state equation. Now, like I always say, if you appreciate this class, your contribution is simply to subscribe at my YouTube channel. Just hit the subscription button and you have really showed appreciation to what I'm doing. And that is, go to YouTube and type in Dr. B chemistry classes and subscribe. Leave your comment there as well, either appreciation or question, they will be attended to. Also, you can like, share as well. You can also go to my YouTube page and also do the same thing by following me, Dr. B chemistry classes, and also liking, commenting, and sharing. Now, today we are going to look at how we can derive very simple that equation, the transition state equation. You must know, like I said, it is used to calculate the rate constant of a reaction and also determine the delta H, which is the enthalpy of a reaction, and also the entropy of a reaction that simply explain the degree of disorderliness of a system. How do we start? By doing that. Let us take a hypothetical equation to lead us. Now, assuming we have an equation A plus B to give us AB, and then it gives us a product C plus D. Now this is an equation. Remember that this equation, we had discussed it in our former class when we discussed the transition state theory. And this is a quasi-equilibrium, while this is the transition state where you have an intermediate product that is formed mainly to overpower the what? The highest energy level state at that particular reaction. Now, to begin, you must understand that in our last discussion, we had said that this particular transition state intermediate product form, even though it can be isolated because it has it's quite unstable and has very partial bonds, it can be isolated, but it plays a major role in the calculation of our rate constant, which we want to do today from this transition state equation. So we begin by looking at the rate equation that defines the transition state. So we will say rate is equals to the transition state, okay? But we will introduce something here which is written in this form, and then we bring in our transition state. Okay. Now, know that this is simply defined as the pre-exponential factor. This is the pre-exponential factor, and this pre-exponential factor is simply explain the frequency to which molecules of a reactant collide. The pre-exponential factor simply explains the extent or the frequency in which or by which the reactant molecules do what? Collide for a reaction to take place. So we will bring it in as a constant. This is the Boltzmann constant, this is the absolute temperature, and this is the Planck constant. They are constants and they have their various figures attached. Now this is our transition state. Now you know why I had said earlier that the transition state play a role in the calculation of the what? Of the rate constant. Now if this is true, we can simply equate this to the reactant. Remember that if you have to draw an equilibrium reaction or equilibrium equation, you are going to put products over what? The reactant. So we can equate this by simply saying that rate is also given. Let us keep this pending. It's also given as K, okay, which is for the quasi-equilibrium, AB, okay, is equals to K, which is for the normal equilibrium of A and B, which of course you know that this is your reactant. Now we can position this to take the form of an equilibrium reaction by considering this as the subject of formula. So it means that K therefore will be equals to this all over this. So we have the quasi-equilibrium or the quasi-equilibrium intermediate, which is the transition state intermediate, all over what? All over A and B. Okay, this now brings us into this reality. Now I want us to understand that this is your rate constant, and usually your rate constant is always calculated from your Gibbs free energy. Okay, it's calculated for the Gibbs free energy. So note something here, that the Gibbs free energy is defined as a root T to the ln of K 55.5. That this is the equation for your Gibbs free energy. Okay, while R is your gas constant, T is your absolute temperature, K is your equilibrium, your rate constant. So we can possibly look for the rate constant to equate it here. So to look for this rate constant, we pull this out. Natural logarithm of K will be equals to what? This all over this. That is minus delta G all over RT. Now, we do not need this constant which describes the molecule of water, okay, that is involved in the reaction. We do not need it. So we can have this. Remember that when we have this equation, we can remove the natural logarithm ln and put an exponential sign this way. Now, to do that, or in doing that, this is what we are going to have. Now, in doing that, we are going to have something of this nature. In doing that, we will now have that K is equals to what? The exponent of what? Minus delta G all over RT. This is what we'll have. When we remove the natural logarithm, we put the exponent this way. Now, at this point that we are here, remember that we said we are not only determining the rate constant from the transition state equation, we are also determining the heat change, which is the enthalpy, and the degree of disorderliness of that particular system, which is our entropy. How do we bring it in? To bring in those two particular parameters, we must also redefine the delta G from the thermodynamic perspective. Now, from thermodynamics, delta G is equals to change in delta H minus T change in delta S. Yes, from thermodynamics, this is what is defined. In order for us to be able to replace the whole of this with this, we are going to divide both sides by RT, because that is what this means. So in order to divide both sides by RT, then it means we are going to have minus delta G over RT, which is this, is equals to delta H over RT minus T delta S over RT. In this case, we can cancel the T here. So we are going to have minus delta G over RT equals to delta H over RT minus delta S over over R. With this, it means that where we see this in equation 6, let us replace it with this. So we are going to replace the whole of this with this. That's what it means. And for us to do that, it means we have k is equals to what? The exponent, instead of the whole of this, we'll put this. Now remember that minus will take the place of here, minus delta h over r root t times, minus here will cancel this minus side that goes to the delta s. So this minus side will cancel this one. So we have delta s over r. Okay. Now at this point, we can simply remove this by equating both sides and making them independent. So by doing that, therefore, we are going to have something of this nature. By doing that, it means that we'll have k is equals to the exponent of minus delta h over r root t to the exponent of delta s over r. See, everything is just simply broken down. Now, at this point, we can simply do what? Rewrite the equation in such a way that we can bring in our pre-exponential factor we started and kept earlier. So we can now say that, therefore, k will be equals to the Boltzmann constant times t over h to the exponent of this. We have removed the whole of this and replaced with this. Of what? Of minus delta h all over r root t, okay, to the exponent of, okay, let us not make it that way. Let's make it easier for us. Okay, so to the exponent of, let's take this, delta s over r, okay, to the exponent of minus delta h over r t. Okay. Now, at this point, you can see that this is your equilibrium constant. This is your rate constant. While this is your entropy, and this is your enthalpy. Okay, this is your enthalpy. You can see that this is the transition state equation. This is the transition state equation. Equation 12 is the transition state equation that will allow you to be able to calculate your rate constant, your entropy, and your enthalpy. Of course, these are constant: the Boltzmann constant, absolute temperature, Planck constant, the gas constant, as the case may be. Now you can see how very simple you can be able to derive the transition state equation from the thermodynamic perspective. Do not forget to like, do not forget to share, do not also forget to do or subscribe. Very importantly, subscribe to my YouTube channel. And do not forget also to go to my Facebook channel, Facebook page, and also do the same thing by following, sharing to your colleagues to also be part of this, and then sharing to your groups to be part of this, and then you like and leave a comment. Until next time.